So you cannot check this blade when it is bent into a circle. So the blades come a lot of times coiled up. You can't check them that way. It'll be a false reading. It'll always be dished on the outside of the curve. Now, what's happening to this blade as it goes through the guides and it goes around the wheel, this term is called anti-clastic curvature, by the way. When you bend something, a flat steel, into a circle and it dishes like this, that's called anti. Anti is because it's the opposite of what most normal minds would think it would do. Clastic curvature, meaning the curvature of the band is changing. And this is spring steel, so when it goes around the wheel, we get anti-clastic curvature in the turn. It straightens out. So the band is like this, and then it goes straight. Then we go around the wheel over here, then we hit a straightaway. And if you picture this like a racetrack, you have two straightaways and you have two turns. And so as this blade is coming through the cut, we need a very flat blade. We don't need a blade that's got a dish in it like this, and we don't need a blade that's got a hump in it like that. Now, because the roller guides are straight, for instance, if I take this straight edge and I put it there on my roller guides, we grind these roller guides true. And when these roller guides are true from front to back, then I can expect it to touch my band all the way across if my band is perfectly flat. Now, when we talk about perfection, that grind is perfect, but the flatness of the steel is not always perfect. So we use a band roller, and you'll see and hear about our band roller in our catalog and in our writings quite a bit. But I need this band to touch in the back edge at least and in the front edge at least. So what we do is, this is the way this would be on the mill, I want 1/1000th dish on the inside of this blade. Now 1/1000th is not truly a dish, but that's the only way I can describe to you what I'm wanting to see. So when I put the straight edge on this in the straightaway, I want to see a hair's breadth. Now a hair on my arm measures 1/1000th, so we're talking about a very small crack of light. But I want this guide to be able to touch in the back to the front. And if I can control the back and the front, the middle will be controlled. Now here is the opposite of that. If I've got a band that I put my straight edge across and it's got a hump, and I'm going to demonstrate that with my hand, I can change this guide all I want, and I'm not getting any difference. This blade then is rocking on the guides. What it does when it hits the wood is it'll hit the wood, cock up, and go down, down into the cut, and that's what we call a diver. You take the band roller, roll it out, and the band's back flat again, it'll just saw straight. So the band roller is a key element. I'm going to go back through the list of 5 things again. We got sharp, we got set, we got flat. That is what the blade has to have. Then we got guides that hold the blade straight away. Then we have band wheels that can allow that band to be controlled by the guides. I want to give you just a quick illustration. If I were to lean my band wheels too far forward, then my blade is tilted down and my guides come in, and I'm going to try to control that, but the front of my blade is floaty. Well, when I hit the log down, it's going to go. So if I was leaning too far forward, the blade's going to dive. If my wheels are leaning too far back, my blade's up like this, the guides still will not control it, and the blade will rise. Now what I'm establishing is the guides can only guide the blade in a limited manner, and that limitation is held and controlled by the band wheels. Well, why is that important? It's absolutely very important. We make our wheels where there's an adjustment. You can adjust them from back to forward, and I'll tell you where we find it to be the almost perfect spot is about 3/32 leaning forward. Now that's a minimum of a 1/16, a maximum of 1/8 of an inch leaning forward at the top. What that does is it wraps the blade a little bit tighter to the roller guide and on the back side, and if the back side don't go down, the front can't go up, and that blade will just saw straight. We can get the fastest feed speed by adjusting those wheels there. And what you might say is that is a perfect spot in the middle, and it will just go straight through a hard knot, just as slick as you've ever seen. Now here's one other thing that I try to describe to people that's very important. If you have a 12-inch cant here and you got some big knots down that log, and this blade is coming along and hits a knot and it rises up. Now a lot of our competitors' mills out there do that, and I hear it daily. I mean, I hear that constantly. And a lot of those mills, they don't even have the adjustment to adjust the wheel so that you can get it right. And that's a bad thing, because then you get the scrap iron is what you get. You have a blade that won't cut straight lumber, you got the scrap iron then. And what is important is to be able to cut straight through the knot. Well, this big knot is here, and it's hard in density, and when we consider how it grows out of the tree, the limb starts growing small and it gets bigger and bigger, and that's how that knot is grown into that tree. Well, blade sawing along and hits the knot and rises up, people will say, well, it followed the grain pattern, and I'll say that it didn't, because the grain pattern a ½ inch up is the same as it is a ½ inch down, and the blade didn't have eyes, so it couldn't see forward, and so if it can't see forward what's ahead, it don't know what's up ahead. But what the blade is telling us is, I can cut this, but 5 degrees upward is where the easiest path of resistance is, and when it can saw 5 degrees upward and go through the knot and settle down, we have to say, well, what did the blade do? Well, it did cut the knot. It didn't say I can't cut the knot. And I always say this, the blade tells a story, and so this blade's telling us a story. It rises up and it says it's easier to cut through the knot this way. It's not that I can't cut the knot, I can cut the knot, but it's easier to go through this hard substance at this direction. Well, why is that direction the least path of resistance? It boils down to, was the blade flat? Are the wheels aligned correctly? And are the roller guides holding it straight away? Those are the 3 factors. I'm going to consider that the blade is sharp and set, because sharp and set is not usually our problem. The problem usually lies in flatness of the blade and the adjustment of the vertical alignment of the band wheel. I've done a lot of talking about the vertical line of the band wheel, and I'm going to just say it this time. Once you get it right, you lock it down, you throw away the key. You don't have to adjust this vertical alignment all the time, so don't let me scare you in thinking you're going to have to adjust these wheels all the time. That's not what you adjust. Once you get that right, the flatness of the blade goes hand in hand. Now, the flatness of the blade will have to be adjusted regularly, maybe every sharpening, sometimes every other sharpening. It's according to how hard you saw and how fast you saw with the mill. Now, there's 3 things changing on a blade as you're sawing, and it's changing in sharpness because we know it's dulling. It's changing in set because it's wearing the set off, and the body of the blade is changing because of the anti-elastic curvature that it's getting as it goes around the wheels, and it's under stress, it's under heat, it's under tension. So these things will change. So we know these things are changing. So when we're sawing down and we hit this knot and it rises up, there is a cure for that, and is to make sure the blade is flat, make sure it's sharp and set, make sure the guides are straight away, and make sure that our wheels are adjusted right. And when those 5 things are correct, it will saw straight through that knot 2 times faster than it ever rose and went through the knot. And you can saw straight lumber all day long when you have those 5 things correct. And that is the most important thing about a bandsaw head. We have other factors that are important. Our drive bearing assembly is built very heavy. We'll get around on that side and we'll show you that. We have nice big shafts so that it can be strong and stout, and shafts not break and the bearings give out. We've gone through all the experimentation and we've got that solved. In the idle wheel, we've got a nice big bearing here. It has 2 sets of rollers in it, actually balls in it, and it holds that wheel stable. We've got a real strong tensioning device with a spring tension. Bandsaw blades are made from spring steel. They need to expand, they need to contract. The spring tension will allow that to happen. When a blade heats up, it expands. We hold the same tension on it with a spring all the time. When the blade contracts, then it needs to give it back. What most people don't understand is, with a spring, when you tension up at the beginning of that blade, it will stay that way. If you run that blade 2 hours or if you run that blade 4 hours, that tension will stay the same and there's no more adjustment. Now, I hear a lot of people with a hydraulic tensioner that does not have a spring, they say, well, how do you know what you got? Because on some of the mills that are out there, they have to tension up, run the blade a little bit, tension up, run the blade a little bit, and tension up again, and that's not a good thing. You want something that you can tension it up and don't worry about tension anymore, and this mill has that. From this point, we'll break away.